operation of rockets exemplifies the conservation of momentum. The increased forward momentum of the rockets is equal but opposite in sign to the momentum of the ejected exhaust gases. This and many other principles of motion, especially in a straight line, rely on the Newton's laws of motion. To have the basic idea on the Newton's laws of motion, please don't go away and stay in focus to this today's lesson. My name is Abdulmajid Talib Khatib, a physics teacher from Susa. Today, through different examples and situations, we are going to study about Newton's laws of motion, where by the end of this lesson, you will get an insight on the concept of inertia, linear momentum and its relation to impulse and collision, and on how they apply to a variety of interesting situations in our everyday life. Before we start, let's talk about an important terminology, inertia. It is the ability of a resting body to resist motion or a moving body to continue moving in a straight line when abruptly stopped. It is essentially the tendency to do nothing or to remain unchanged. We can also define inertia as the resistance of any physical object to any change in its state of motion. This includes changes to its speed, direction, or state of rest. It is the tendency of object to keep moving in a straight line at constant velocity. The more mass of a body has, the greater its inertia, and vice versa is true. A 1,000-kilogram car has higher resistance to oppose motion than that of 800 kilograms if the same force is applied to them. From one among the definitions that we have seen, we have three types of inertia, which are inertia of rest, inertia of motion, and inertia of direction. By inertia of rest, we mean that resistance of a body to change its state of rest. That is why a stationary body requires force to make it move. The force is needed to overcome the resistance of that body so that it can move. Inertia of motion is the resistance of a body to change its state of motion. For instance, a passenger sitting in a bus tends to fall forward when the bus suddenly stops. This is because of inertia of motion. The upper part of the body resists stationary state, continue to move. The third type is inertia of direction, which is the resistance of a body to change its direction of motion. A good example of inertia of direction is our protection through umbrella. The raindrops falling vertically downwards cannot change the direction of motion and so cannot wet us when the umbrella is up. Another example is tangential movement of untied stone. This happened when a stone tied to an end of a string is whirled, and if the string or thread suddenly breaks, then the stone flies off along the tangent to the circle. This is due to the reason that the pull in the thread was forcing the stone to move in a circle. As soon as the thread breaks, the pull vanishes. The stone moves along the straight line tangentially to the inertia, due to inertia of direction. After having some insights on the inertia, Newton proposed a law concerning inertia of a body. This is called Newton's first law of motion, or the law of inertia, which states that every body continues in its state of rest or uniform motion unless external force acts upon it. That means if a body is at rest or is moving with constant speed in a straight line, there is no net force acting on it to make it move or stop from its motion. The first law is called the law of inertia because of the unwillingness or the resistance of an object to start moving or stop from motion. The object of low inertia is easier to accelerate than that with a larger inertia, larger mass. The motion of an object is mostly dependent on its mass and velocity. Momentum ties velocity and mass into one quantity. It might not be obvious why this is useful, but momentum has this cool property where the total amount of it never changes. This is called conservation of momentum, and we can use it to analyze collisions and other interactions. Mathematically, momentum is the product of mass of a body and its velocity. If a body of mass m is moving with velocity v, then we have linear momentum P equals m times v. As it is the product of mass and velocity, the SI unit of momentum is kilogram meter per second, and it is a vector quantity as it has both magnitude and direction. The mass of a body is constant, therefore the momentum of an object will change if its velocity changes. That is, the object has to accelerate under the influence of a force. The greater the force applied to the object, the greater the change in velocity, and hence the greater the change in momentum. If the applied force does not cause changes in momentum, then the body remains in its state. This is in accordance with the first law of motion. So the force that causes motion change is the unbalanced force or net force. Mathematically, we say that net force is directly proportional to the rate of change in momentum. If Pf is the final momentum and Pi is the initial momentum, then we have net force F equals Pf minus Pi over T. This is the statement of Newton's second law of motion, which gives the relationship between force, mass, and acceleration of an object. We have net force F equals K times change in momentum over T. If K equals to 1, then we have F equals change in momentum, Pf minus Pi over T. But Pf is equal to mass times the final velocity, and Pi equals the mass times initial velocity. Then F equals m times v minus m times u divided by t, so that we have m into v minus u over t. But v minus u over t is the acceleration. Therefore, we have F equals m times a. An alternative statement of the Newton's second law of motion states that the rate of change of momentum is proportional to the applied force, and it takes place in the direction of a force. Hence, the Newton's second law of motion can be summarized as the force is directly proportional to acceleration of the object. Also, for a given force, the acceleration of a body decreases when the mass is increased. We can say that the acceleration of a body is inversely proportional to its mass. If a mass of 1 kilogram is accelerated with an acceleration of 1 meter per second squared, then the force of 1 Newton is said to be acting on it, and we have the definition of 1 Newton. The force which, when acting on a body of mass 1 kilogram, it produces an acceleration of 1 meter per second squared. Example: a car of mass 1000 kg is moving with a velocity of 60 km per hour. What is its momentum? Here we have been given the mass of the car, which is 1000 kg, and its velocity v 60 km per hour. To find momentum, we use the formula P equals m times v, but v is given in km per hour. To change it in meter per second, we use the relation that is 6 km per hour equals 10 meter per second. So that velocity in meter per second, 60 km per hour times 10 meter per second divided by 36 km per hour, which gives us approximately 16.7 meter per second. Therefore, momentum P equals 1000 times 16.7, which is 16,700 kilogram meter per second. Another example: a tennis ball whose mass is 150 gram is moving at a speed of 20 meter per second. It is then brought to rest by one player in 0.05 seconds. Calculate the average force applied. Here we have the mass of the tennis m equals 150 gram, which is equal to 0.15 kilogram, the initial speed u 20 meter per second, and the time t for which the ball changes its velocity from 20 meter per second to 0 meter per second as it comes to rest in 0.05 second. That we have also the final velocity v, which is 0. So to find the average force applied, we use the formula F equals ma, or m into v minus u over t. And by substitution, we have F equals 0.15 into 0 minus 20 over 0.05, which is 60 Newton. Therefore, the average force applied is 60 Newton, which means 60 Newton of a force the player should apply to stop the tennis ball of 150 gram, which was moving with 20 meter per second. Note that momentum is a measure of strength and a measure of how difficult it is to stop an object. If you have ever kicked a ball, hit a punching bag, or played sports that involve any kind of ball, you have been using the concept of impulse without even knowing it. So what is exactly impulse is, and what does it have to do with any of those situations? How is it related with momentum? Or rather, how is momentum related to impulse? When a force acts on an object for a short time, impulse is the measure of how much the force changes the momentum of an object. From F is equal to rate of momentum change, then we have impulse J equals F times T, or change in T. Because impulse is a measure of how much the momentum changes as a result of force acting on it for a period of time, an alternative formula for impulse looks like this. J equals change in momentum, which is Pf minus Pi. This formula relates impulse to the change in the momentum of the object. So we can define impulse as the product of force and time interval, or it is the change in momentum of a body. Impulse has two different units, either kilogram meter per second or Newton second. For instance, in the previous example, if we to find the impulse, just we use the formula J equals F times T, which is 60 Newton times 0.05 second. And the result is 3 kilogram meter per second, or 3 Newtons second. This means that momentum changes by 3 as a result of 60 Newton applied to a tennis ball for a period of 0.05 second. Note that the forces that act over short time intervals are called impulsive forces. Let's stop here. Don't miss the next session where we are going to learn about Newton's third law of motion. Thanks for watching.